All right, welcome to your next unit where we're going to be talking all about chemical reactions. So we need to look at chemical equations then. So in all these chemical equations, you're basically going to be converting one or more substances into another substance, okay? You're not getting rid of the parts, you're just changing it around. So I like to think about it like baking, okay? If I'm going to bake a cake, I need certain portions of certain things like flour, milk, butter, sugar, probably some vanilla or some chocolate, depending on how good I want to make it. I need different things like that in certain portions in order to make a cake. So I have my reactants, my ingredients, and I have my product, my whatever I'm baking, right? And so this works throughout, and we need to think about this like in the chemical sense. So here's how plants work. They use the energy from the sun, and they mix that with carbon dioxide we breathe out, plus water from the earth, and they bake it up, and they end up making sugars or glucose, which we consume and the plant consumes for energy, and it releases oxygen that we can breathe. O2 specifically is the type we can breathe. And so this is the recipe, if you will, for glucose and oxygen that plants use in photosynthesis. It's also the chemical reaction that happens. Now, it's important to remember that all things follow the law of conservation of mass. One of the overall fundamental things in all the universe is you can't really you can't create or destroy matter, right? Everything that is has always been, it just changes form over time. And that's exactly what we're doing in a chemical reaction or equation is we're changing how it's arranged. And sometimes that dramatically changes how things can affect us. Think about something as simple as, say, table salt, right? If you've ever seen table salt, that's just sodium and chloride. Sodium chloride is table salt. Well, that's made from sodium, which is a metal that actually ends up blowing up in open air containers, plus chlorine, which often forms a gas. And so it is actually a toxic gas that comes out that can actually kill you. So something that blows up and something that can kill you in a gas form come together to make something we consume every day that's really enjoyable on our food. Completely different from what it started with. However, you're going to get the same amount. So look at this example of water. This is unbalanced up here with sodium, by the way, but we'll look at that in just a second. So here's a balanced equation of water, looking at the actual molecules. First, you have some hydrogen. You have 4 hydrogen, and it comes together with 2 oxygen, and it forms 2 water molecules. Each water molecule has 2 hydrogen and 1 oxygen. So essentially, you start with 4 hydrogen, you end with 4 hydrogen. You start with 2 oxygen, you end with 2 oxygen. And so this could work. Up here, this couldn't because I had 1 sodium here, 1 sodium there, 2 chlorine here, and only 1 here. So essentially, I have all the ingredients that I need to make a cake. I just don't have the right proportions down. And so I'm going to have to change this, but I can't just take away some of my ingredients that I have because chlorine like this comes together with 2 of them. So I'm going to have to change the overall yield as well as the amount of ingredients that I put into it. We do that by adding coefficients. So the number in front of the molecules that we're using, these large ones that are highlighted in blue here on a typical chemical equation, that's telling me that I'm increasing the entire amount of the molecule. Notice I'm not just doing 2 potassium for this one, or 2 iodine, but 2 of the potassium iodide. Now, there's a couple of things to notice in this equation to be able to read it correctly. So you should understand what some of these things are, like lead and nitrate. Notice nitrate is a polyatomic. Lead's a metal. This is usually ionic. And so they come together to make lead-2 nitrate. Well, if we have this, then that means there's 2 of the nitrates. So you do that 2 times everything in parentheses. And so we already are using 3 oxygen for every nitrogen. So this really means we have 6 oxygen and 1 nitrogen here. And then we just have 1 lead. That's the recipe that you needed just to make the ionic bond of lead 2 nitrate. If I wanted to increase that in my formula though, I don't add these subscripts. These subscripts are locking this molecule in place. This is a molecule we want to keep that way. The same with this. This is potassium and iodine, making it potassium iodide. So we wouldn't want to change up these two different things going together, because that's what makes that ionic compound of a metal of potassium, 1 metal of potassium, 1 nonmetal of iodine, makes potassium iodide. But I'm going to need more over here, because you can already see there's 2 iodine in this molecule. So if I do a coefficient, that multiplies by every part of that molecule, meaning that I'm getting 2 potassium and 2 iodine. Over here, this one multiplies by everything in the molecule. So I would get 2 potassium, 2 nitrogen, and 6 oxygen, because I already had 3 of them. If I were to put a coefficient over here in front of this one, I would have to multiply oxygen by whatever the coefficient is, but also by whatever its subscript is outside the parentheses. So if I had a 2 in front of this, I would actually end up with 12 oxygen just from this one molecule. But you can increase the amounts of like the whole molecule you're putting in, but you can't change the proportions within the molecule. Something else to notice, this AQ, notice it's all lowercase. Capitals indicate elements. So when you have a lowercase only, that's just a note to whoever the scientist is to tell them this is an aqueous solution. Aqueous solution means that this has probably been dissolved in water. And so these are dissolved in water. This would end up remaining dissolved in water. But this is an S, meaning a solid. So we would call that a salt. It precipitates out of it. Here's kind of a cheat sheet giving you what all the different little formulas tend to mean in these type of reactions. So our yield symbol, it means produces. It's just an arrow. It's telling you which side is the reactants, which side is the products. It'll always point to the products, okay? Plus is very simple. It means that this is put in between different molecules or atoms that we are combining or that we get out of it. And then these are those notes. We already looked at aqueous solution, so it's a solid dissolved in water. S is for a solid. We say it's a salt a lot of time coming out of it. And then there's liquids and gases that are also produced. We talked earlier about 2 chlorines together making a gas, so that could come out of things. There's certain chemical reactions you can do which will bubble, and you know that it's causing a gas as one of your products. And then if you see this little triangle on top of the yield arrow, it means the reactants are heated. So a lot of times it's used with things to indicate the energy that's used for it. It has to have reactants heated in order to produce it.